All right, welcome back. I mean, I say welcome back to whoever may be watching this. That's a big maybe. I hope this one goes a little shorter than the others. But this is going to be in a new playlist, and we're talking about chemistry, so I'm also taking chemistry. So this will be the sort of first general concept in chemistry that we covered in my course, Kinetics. And we're just gonna do a video talking about some general aspects in kinetics and just some equations and stuff. So kinetics really is the study of rates. That's the most important thing. So it is the change of something over a change in time. Typically, chemically, we use like a change in moles. Oh goodness, this happens every time. We use a change in moles, so a change in moles, a change in time. That's say like a rate of equation. Because in an equation you have like A goes to B, or B plus C, or whatever. And then you have equilibrium systems sometimes that go backwards. But kinetics really is the study of rates. That's what you need to remember. We're always dealing with rates. So there are four sort of things that I wanted to talk about, which I found are fairly important for rates. So we'll talk about the actual rates themselves, the rate law in sort of general forms, the units, which are incredibly important for working stuff out and working out problems, and the methods involved in rate law calculations. So these two topics are very, very linked, and rate law is of course linked to this one. They're all very, very interrelated, and rate law rates just applies to everything. So let's first talk about rates. So let's consider this reaction A plus B produces C plus D. So actually I'll write that a little better with some coefficients just so it's easier to understand. AA plus BB produces CC plus DD, right? So in this reaction we have these reactants being consumed and these being produced. So we'd expect the change in A over the change in time to be a negative. It's consumptive. There's a consumption of the product of the reactant going on here, and the amount at which it's changing can be standardized by this formula. If we look at this equation, we can standardize it by saying 1 over A, and then we do D. So we use this notation dA over dt. It's the derivative of A, basically. So it's the rate of change of A by time. So as time changes, so does D change. So D, and then we talk about concentration. Molecular concentrations are very important because they tell us like how many moles we have. Change of A, dt, equals rate of change of A and B. dB on dt equals 1 on C dC dt equals 1 on D D on dt. So these equations, so we have products and we have reactants. So since they're reactants, we give them a negative sign. Now, technically, this is important to remember. You can't have a negative rate. So mathematically, what a negative rate just implies is that a product is being consumed, but we can't say that the rate is, in a statement, the rate is negative 0.44 moles per liter, because it doesn't really make sense. So we say there's a consumption of the product. So let's say the d of a dt is equal to negative 0.5. Then we say, and this is the reason we put the negative sign there, so this turns into a positive. So we say that A is consumed 0.5, and we'll do mole seconds. A is consumed 0.5 moles per second. And if there's a positive rate, of course it's positive. dc is formed 0.5 moles per second. This is just important to bear in mind when we're looking at rates. Yeah, that's about all I kind of wanted to cover for rates. That's all that's very necessary. This is a general rate equation. It's this thing because it generalizes this entire formula into things being produced and things being consumed. So that's kind of what I want to talk about rates. So let's talk about rate laws. Rate laws it's a fairly large topic. So we're gonna draw a little heading up here. So rate laws. There's a general form of an equation, which is the rate that an equation goes forward is equal to a constant K multiplied by the concentration of here, let's draw out a reaction to make it easier to understand. AA plus B produces CC plus DD. This is like a basic reaction. Produces is K. So that's the reaction constant. We'll talk about that in a moment. Of A raised to a power and B raised to a different power. They could be the same, but we don't know yet. So this is called a rate law with a rate constant. So let's just go through each component. So we have the concentration of A and the concentration of B. These are just concentrations. Then we have N and M. These are called reaction orders. So the order of the reaction determines the units that are sort of occurring in this reaction, because let's say this is an important thing to remember about units. Units are squared when quantities are squared, because quantities that have units, let's say A is M units, so units squared, it turns into A squared M squared, because the units are also squared. So the order determines the units of the rate, and the units of the rate constant too. So if you have a rate of a certain thing, this also allows us to tell with the rate constant what the units are, and we're gonna talk about units in a second. But this rate law is very important to tell. So Nk is equal to the rate Sorry, it's not working. Rate constant. Now, it's very important to remember that n and m must be experimentally derived. And this sort of talks about equations. This is talking about chemical equations. Chemical equations written out overall are quite vague because they just express what happens in general. Like we can have, like for example, H2O plus CO2 producing C6H12O6 plus O2. So we can have these sorts of equations. This will be, is this accurate? Yes, 6. Oh, and this will be 6 as well. We can have these sorts of equations, but these equations are multi-step and they're very complex. A lot of stuff goes on in these equations before we actually do, like, before we have the overall equation being represented. I'll just check something real quick. So let's say we have a reaction like well, like this, for example. NO2 plus CO2 as gas produces NO gas plus CO2 gas. So we have, sorry about that, zoom in. I got something on the screen, sorry about that. We have 2 NO2 gas. Like there's a chemical mechanism that sort of goes, that allows this process to exist. So we have one step here. NO2 gas turns into NO3 gas plus NO gas, and then NO3 gas plus CO gas turns into NO2 gas plus CO2 gas. So these steps are what are called elementary steps. They're steps that happen because the collisions can occur, but these steps, they're called elementary because they're very simple. Like one thing happens. I mean, this thing decomposes, but they form the overall action that allows this equation to happen. So they're like simpler steps overall that form this larger equation. And the way that we have this larger equation forming is that we can cancel out these. Like if you look at NO3 here, they're called intermediates. So NO3, it's an intermediate of the reaction, and that means that it's basically like it's produced and then it's consumed over the course of the reaction, because these reactions are complex and they take up many steps. So yeah, cool. If you understand that, I'm very happy for you. Okay, so here's an important thing to remember with elementary steps. The order of the equation, remember we said that was experimentally derived for overall equation. Order for the elementary steps can be assumed from the stoichiometry. So the rate of, let's say, reaction 2, let's work out the rate. So the rate is equal to K, some random constant, times the concentration of NO3, and times the concentration of CO. And that works out. Let's say we had another elementary step which looked like, let's say, 202. This is just completely random. 302 turns into 203. I don't know if this is something that actually occurs, but let's say it does. So the rate of that is equal to that K. So this is a new number. It's just a random K. And then O2 to the third power. So that's how the stoichiometry affects it, right? You can raise it to the third power. You can assume that order is to the third power. So it's a third order equation. So let's do this here. Overall equations must have orders experimentally derived. See? Very nice. That works. It's just the case that the equation is very complex, and so we can't make any real assumptions. Sometimes the equations are simple, and their order is just like their stoichiometry, pretty much. But we can't make any assumptions, right? Because we want to be fairly accurate. If you have this equation here, this overall equation here, then you can't assume anything about it. You don't know really what the order is. Yeah, so that's kind of what I wanted to touch on with rate laws. There's one other thing that I wanted to mention, which is that when we have a rate law, we assume the concentration changes of if they're gas and aqueous. So if we have solids and liquids, concentration is assumed to be 1. Therefore, they don't factor into the rate law. That's just something you have to remember. Basically, their concentration doesn't change because, like, for a solid, it's like a thing that just exists, right? So, like, per liter, it just exists. And with a liquid, like, it sloshes around. I'm sure there's a more technical definition, but it's just assumed to be 1. So that's kind of what I wanted to talk about with the rate laws. Okay, so we understand rate laws now. There's one other thing. So let's think about these elementary steps again. This is just, I'm going to say this. It's not incredibly relevant, but just remember this. Like, certain reactions are, the term is unimolecular, dimolecular, trimolecular, think that they have actually other names. But basically, if you have one molecule going into two molecules, there's like one interaction that happens, it's unimolecular. If you have two, then you have, like this step, for example, then you have like a dimolecular. And that involves two things coming together. So if you think about reactions, they're actually like fairly complex. So you need to have right energy, right orientation, and you need to have right and you need to have collision itself. So as long as you need these three conditions to have a reaction, because without it, the reaction won't actually occur. So if you think about this, like this reaction, this singular one, is more likely to occur than this other one, because they're like, it's harder for them to bump into each other than for this one just to exist and to spontaneously go, oh, blup, and turn into these two NOs. Yeah, for these, actually this is a dimolecular as well. My apologies, because it's two molecules that are just forming together and then splitting apart, so this is also dimolecular. But if you had like a single interaction when you have go A to B plus C, then you have a unimolecular. A unimolecular elementary step, and that's like, I mean, it happens, it just decomposes into B and C. That's just how it happens. Trimolecular is very rare, because you'd have to have A plus B plus C turns into, whatever it is. This, three molecules colliding at the same time, the right orientation with the right energy, it's like, it's very unlikely. And then quadrimolecular, I mean, what are you going to do? 4 particles all at the same time? I mean, these sorts of things don't happen. And this is why we have elementary steps in the first place. Like, these sorts of interactions are just unlikely. Some of them are just like, this one bumps into this one and then turns into these two. It's unlikely. So that's why we have these steps, because they're actually how the reaction proceeds. Okay, so we talked about rates, we talked about rate laws. Units. Okay, so let's think about units. Let's say we have a rate, and we have A plus B turns into C, and this is elementary. So the rate is going to equal to K A times B, like this, and they raise to the first power because that's how the elementary step works. So if we think about so when we talk about order, we talk about the order overall, so it's the sum of the orders of the reactants. So this equation, let's call it 1. So 1 is first order with relation to A, concentration of A, concentration of B. Here, I'll make this more clear. And also first order with relation to the concentration of B. So we have first plus first turns into second order overall. So when we talk about units for the rate constant especially, here's how the system sort of works. So we have zeroth order. So what zeroth order implies, this is very important to remember, nothing affects, well, K affects it, but basically reactants do not affect the rate, right? So zeroth order, you have K in terms of units of molarity per second, right? First order, so you have some reactant, whether it's one reactant or multiple, that affects the reaction. So we have K in terms of per second. Second order, we have K in terms of 1. Oh my goodness, it's trying to solve for no reason. And this is molarity, it's per molarity per seconds, right? Per molarity seconds, basically. That's how you would say that. It's equivalent to this. I don't like how this is written out. But you can also write it as, and this is especially heinous in my opinion, molarity -1 per liters. Technically by convention, probably right. Liters, molarity -1 seconds to -1. It's pretty awful looking. But if you remember this pattern, so it starts out m divided by s, and now you divide by molarity. Divide by m, it's moles per liter, every additional order. So we know the units of the rates, like third order. So K equals 1 over m squared s. So let's say I have like the sixth order. So we have K is equivalent to 1 over, and we've got the third order, so it's going to be m to the 5s, right? Because we're kind of countering, so you're thinking the original form is m over s, and we're dividing it by m to the amount of orders. So it equals 1 over m to the 5s. That's sort of how it is. It's there's always this time, because time always changes like rate. The rate constant has to make the rate make sense. So the rate, like it can be in like fairly random units sometimes. The rate can be like meters, seconds, something like that. But sometimes, but yeah. Yeah. So that rate constant allows you can tell what values your equation are if you know the rate constant values. So you know, like if they give you like moles per liter per second, you know it's going to be zeroth order because it's moles over seconds. That's the important little thing about units. Okay, and now we're going to talk about methods. So basically, you have kind of three ways of going about this. You can either do experimentally, you can determine the rate with the equilibrium. Oh, sorry, it's called the pre-equilibrium approximation. And then you have what's called the solid state approximation. So these are three different ones. Of course, this one experimentally is completely different to these two, because these two are like mathematical. So experimentally, you calculate the rate, and then you sort of go onwards from there. You can determine like the values of k, because since k has some sort of like there's a formula you can work out generally. If you have an equation that doesn't change b from one condition to another, and you can measure the rate, this k is going to be the same, and this b is going to be the same, so you can calculate for a, since a is going to change, and vice versa. If you keep this constant and you change this one, then you can measure that change if you know the rate, because the k remains the same. So that's sort of the experimental process. Now, pre-equilibrium approximation. So remember elemental steps. We can sometimes have a slow step. So a slow step determines the rate. It determines the rate of the reaction. And like if you have a slow step, let's say in this mechanism over here, where is it? Just talking about this. That's in rate law. In this mechanism over here, if you remember, let's say this is the slow. So let's write that out there. Hope we can remember this. Turns into no, I got that wrong, sorry. What was it? 2NO2 turns into NO3 and NO. Okay. So if you have this, and this is the slow step, and it's elementary, and you can say, because the slow step determines the rate of reaction, you can't go faster than the slow step. So think about it. Think about it like this. Basically, I can't. Or there's this very cool metaphor. The weakest link in the chain ultimately determines the strength of the chain. You're no stronger than your weakest element, because that element always breaks first. So this is exactly the same. The slowest rate, the slowest equation determines the overall rate of the equation, because we cannot go faster than that rate. So the rate here is equal to K, concentration of NO2 squared. Right, so that's our overall rate equation. That's what we use as a pre-equilibrium approximation, because this is slow step. Oh no, sorry, my apologies. This is just called a rate determining step. I've got this mixed up. I know I was missing something. So this is the rate determining step. This is very easy. This is easy to understand. So SSA, and then we have as well the pre-equilibrium step. So let's say you have a like a fast, like you have two elementary steps. So you have a equilibrium plus a completion, like a reaction that goes to completion. So ultimately you have like three equations. You have the rate, let's say this is K1, and the reverse of the reaction is going to be K to the -1, and this is K2. So you have rate equals, and you have three equations. One that's in terms of K1, rate in terms of K to the -1. Because the equilibrium is like very important, fast equilibrium, since both of them are fast at reaching equilibrium, then their rates are quick. We can just say that their rates are pretty much the same. That's why it's an approximation. So we can say that they reach the same time, basically. And then we have rate equals K2. And then it's something, it doesn't really matter. The point is, these two are equivalent. So we can have K to the -1 equals K to the 1. Because the rates are effectively the same because of... they've got like formulas. It's not very important. I mean, eventually it'll be important. Because of... Oh, and this has to be the slow step. Because of the like fast equilibrium, these equations are the, like, they can be the same because the rate of reaction forward is equal to the rate of reaction in the reverse direction. Right? I hope that makes some sense. This is just conceptually, really. You gotta search this up to get some good questions about it. But the one thing we really need to stress about why these methods are necessary is that in the rate law, we cannot have intermediates. We can't have them. It's just not, like, intermediates are unmeasurable. Like, we can't measure unless it's hydroxide and H+, because those molecules are measurable through pH, but we cannot measure intermediates. Like, you can't tell if, like, there's a, like, COH is an intermediate. We can't tell really the concentration of COH in this equation because it gets consumed. So we just know it exists there. But the whole reason we have these pre-equilibrium approximation, this solid state approximation, is because we can't have intermediates in our rate equations. Let's look at I think in this one. Yeah, look, if we assume this is the slow step, then this is an intermediate because it's actually no, it's not an intermediate. No, this one is not an intermediate. But let's say if we said that my apologies. CO. Trying to figure out how these... Might have been rambling on a little bit. I didn't explain these elementary steps quite too well. Sorry, it's supposed to be CO gas here. Let's say we had this equation here as the slow step. Then NO2, NO3, these are intermediates. They wouldn't be possible in the rate. Like they're not measurable, so we can't really do anything about them. So the way we try and get rid of them is this pre-equilibrium approximation, which gives us three rates. And once this slow step has an intermediate, then it's like we have to use this pre-equilibrium. As long as we have a fast equilibrium, that's very important. Now SSA, this is like when you're completely lost. So this sort of equation is like, it occurs, I mean, we can use it to determine a rate. Because it just assumes certain things about a, like, how do I say? About an equation. So, like, let's say we have this sort of equation which looks like what's a good example? Okay. Let's say we have A plus B tends to C, and then C tends completion into D. So this is an intermediate. So we don't know the step. So let's, what we say about intermediates is that they're usually consumed. So the rate of change of their existence is pretty much 0. Hold on, let's do this with the derivative notation. dt equals 0, pretty much. So the consumption of this, concentration of time, that makes no sense. T is equal to the rate of production plus consumption, because these rates are like negative rates, basically. They exist as negative, so we minus them. It's like minus in convention, but they're being added, basically, but they're negative sort of things. So let's put negative, because these things are going to exist as negatives anyway. Okay, so we have K1, K2, this is not K2, this is K to the -1. This is K2. And now, let's look at this. So the rate of change, we assume is 0. So 0 is equal to the rate of every time that it's produced. So it's produced in this equation, K1, A, and it's raised to the, because it's elementary steps, they're raised to the powers, minus K to the -1, because it's being consumed in the reverse reaction of C, minus K2, because it's being consumed, D. See? That's sort of how we work this out. So let's rearrange real quick. K1, A, B equals K to the -1, C minus K to the 2 over D. Right. So then what we've essentially, this is D, because this is consumed. sorry, my apologies, C, because it's consumed in the same way. So K1 A B equals, let's do a little bit of maths, K to the -1 plus K to the 2. Now this is very important because we need to sub out like intermediates. We need concentrations of intermediates. So this is the way that we sort of find them. We use them in terms of definite terms. Like in this reaction, this will exist and these two are not intermediates. So look, we have concentration of C out here. So the concentration of C is equal to the K1 A times B over the C1 plus C2. Yeah. Now there's also one more thing. So this last step is we're going to work out the rate of change of D. So D of T, sorry, I'm supposed to draw that correctly, is equal to K2 multiplied by C. So this is why, so we work out that rate ultimately, and that's like the overall rate of the equation as well. So now we have C. That's the entire reason we did this nice escapade up here. It's because we want to work out C. So D of D dt is equal to K2 K1 A and B over K-1 plus K2. And so it all works out. It's very nice. And that's our rate law. And that's what the solid state approximation comes out to. Ultimately, this equilibrium pre-equilibrium approximation does the same thing. It's just that we know that there's a fast equilibrium here. And we don't know anything about this equilibrium here. So this is just like a longer method. Because we can't assume anything. And we don't assume as much in this method. Only this assumption, which is pretty much true anyway. Yeah. So we could have the same reaction if we knew that this equilibrium is fast. Then we could do this pre-equilibrium approximation. We might get a different result, but ultimately, as long as the concentration of the products are consistent across both, they should predict pretty similar things. Sometimes they predict different things, like the maths doesn't work out always. Sometimes they're different things, but sometimes these are similar and sometimes these are different equations. That's just what you have to remember. And just the methods, just remember the methods realistically. So yeah, that's a pretty basic overview of kinetics, rate laws and equations. Now there's one more thing that I need to cover. So you see rate. So rate is equal to the derivative of concentration over the over time, right? So if we integrate this rate, then we have an equation for concentration at time, right? So there are certain like integrated rate equations. There are different ways to do it. Like there's a method to derive all these. Let's say we have a first order equation. So rate equals K A, right? So this is derivative of like A over D of T equals K A. So if we want to integrate this with relation to time, it kind of looks like this, derivative of so it's kind of like it becomes ln a equals kt plus ln of the initial approximation, initial concentration. It's very important. It's just the way it starts out. The graph always starts out at some point, and that's how we sub in the point. So this is the integral first order integrated rate equation, because it's just taking this and integrating it. So this is first order. So when we graph the equation, we should expect that the concentration of A is linearly linearly like proportional to, is directly proportional, I should say, to the, so the log is directly proportional to the time, because as time increases, it should be a straight line basically. If we plot just concentration, it's going to look kind of strange. It's going to look like a bit of a line. But if we plot the log of a first order equation, it should be like rough. It should be pretty much, you know, spot on that it is the log. If we look at zeroth order, the rate equation looks like this. Sorry, it's not ln. Because of the way it integrates, concentration of A is equal to KT. Actually, let's do the integration just for integration's sake. So yeah, if you see here times here, so A equals KT plus, so this should be a straight line. Should be a straight line that we get if we map the concentration, because it means that it's, the concentration is not the rate isn't equal to the that equation. Sorry, there's one more thing that I needed to put in there. Right. These are all negatives actually, because this is a rate of consumption. So you see, this is negative. So it's negative. The way, so we should expect first order, if we plot concentration versus time, then we should get a line of like concentration versus time. So yeah, concentration versus time. Cool. And then there's first order. Second order, sorry. And that is, let's just do the integrated rate, because it's kind of annoying to do the equation which leads to this. So this is positive. The reason is because of the way the integration works. So if we plot 1 on A versus time, then we should get a straight line. So that, like, if you get a question like this, if you get asked to plot like to determine the order based on some sort of like concentrations. If it's zeroth order, you can plot it and get a straight line, so your gradient will be like consistent throughout the entire, like all the points on that graph. If you get first order, then it should be consistent with L and A, and if it's second order, it should be 1 on A. That's what it's consistent with. Yeah, so that's about everything in kinetics. I'm not sure if there's anything else that should really talk about too much. These are the main things, and most of the sort of things can be asked at these questions. Yeah, so thanks very much for watching, and I'll see you in the next one.